One of the topics that's extended all semester is Big O. We introduced this certainly in the first couple of lectures, and we're wrapping up with it now. And so I wanted to do kind of an overview of the topic of Big O for us. What it is, Big O is a way to measure algorithm complexity, typically either in terms of time or space. We've focused heavily on time, but space is, well, it's not as common, but it's not uncommon. Why we use it: it provides a quick way to assess whether an algorithm makes sense in a particular context, often related to the size of a particular input. So we can answer questions like if we have a sort in our process or nightly processing, and our nightly processing is taking maybe 4 hours, and we say, well, what happens if we add yay many additional things that we have to sort every night, perhaps customers? We can do a quick estimate on how much longer it's going to take. Okay. We can point out bottlenecks that encourage us to choose or consider different approaches. Once again, if there's a story about a company that was sorting, had a sort as part of their nightly processing, and they were looking at putting a lot of money into buying new hardware for that. And what ended up happening is they brought in a consultant who looked very broadly, and he realized that for what the company was doing, that they basically wanted to group customers by zip codes anyhow. So part of the sort was sorting on zip codes, and then within that, customer names. And he set up a series of post office boxes at the local post office to group things so that all of the mail from a particular from customers in a particular zip code would go to a particular postal box. And the result was, instead of one big sort, he had a much smaller sort for each customer zip code. And the thing is, if you think about sorts, if you can break it into groups, even fairly large groups, instead of one single big group, things can get a lot faster. Okay, you don't have that n squared thing or even the n log n thing beating up on you. Also, just we can look at our processing and say, we're not sure why this is so slow, but as we look at the different pieces, we realize, oh, here's a piece where we're doing something that's in a nested loop that's not a particularly quick nested loop, and that means that it's going to be n squared. And so as we've grown, this has become more and more important, and it helps us to find those things. Finally, it can help us to avoid futility. There are some problems that simply get very expensive to solve, and so we might want to consider whether we actually have to solve them. Classic example is the problem of class scheduling. You might say, wouldn't it be nice if we simply let students pick their courses, and then we pick times where they didn't interfere with each other so that nobody would have a problem with a time conflict? Well, it sounds nice. It turns out that this is actually a variant of the knapsack problem, which we've seen in terms of the box packer, but without a lot of extra boxes to go to. At any rate, long story short, the big O on this thing, to do it optimally, to make sure that nobody has a class conflict, you have to compare all the possibilities, and that's an n factorial algorithm. And of course, given even a small college the size of Covenant with 1,000 students, running an n factorial algorithm means it's just going to take too long. And so we just don't do that. And there are plenty of people out there that have educational software. For instance, the people that make Banner. And no doubt they've looked at the sort of thing. They've had people have said, gee, wouldn't it be nice if you would solve the scheduling problem for us? And they're aware that you look at it and you realize you run into this n factorial situation, and you go, this isn't going to be useful to write the software because it's going to take too long. Or another example, companies that have to solve the traveling salesman problem every day. For instance, UPS or FedEx in scheduling customer deliveries, right? What's the best order for the van to go dropping your stuff off at? Well, it's an n factorial problem. Do it optimally. So what you probably do is you probably do something like a greedy approach, and you just figure, well, that's pretty good. That's good enough. That's going to be within 5 or 10%. And there are some somewhat slicker ways of doing it that schedule. It's not quite optimal, but it's much closer to optimal than we would get with the greedy approach. And there are now companies that sell software that do that. And if you're FedEx or UPS, that might be worth paying quite a bit of money for if you could run a lot of your routes through it. Because even if you only save a little bit each delivery, it adds up at some point. But simply saying, oh, we're going to do this optimally, well, not so good. So we can avoid futility. So we use it so we can do a quick assessment of an algorithm. We use it to find bottlenecks or consider approaches other than just buying more hardware. And we can use it to avoid futility. So those are things that it's useful for. So it's become a very useful concept. Google really blew this up in that they started asking their job applicants a lot of big O questions. And you can debate whether that was really a useful thing to do or not. But they did, and they think it's useful, and they've been doing okay. On the other hand, Google has a reputation for hiring PhDs from Berkeley and Stanford. And those people, they're academics, at least in part, and they just think it sounds neat to work with big O's. So you can debate how useful that really is. But what I'd like to point out is what should not be. It's not a way to avoid benchmarking. If you really care about the number of processor cycles that something's going to take on a particular piece of hardware, you need to run benchmarks. You need to actually run it and see how long it takes. You need to not look at big O's. Now, the big O's can say, well, these are the approaches that are worth benchmarking, and these approaches are not worth benchmarking. But some people want to try to make it more and more detailed until it's trying to substitute for a benchmark. It's not what it's designed to do. It's not what it's good at. I actually had an advisor, a first advisor, and as I tell people, having a first advisor is kind of like having a first wife. It indicates something went wrong, and it did. But one of his projects, it wasn't his main project, but one of his projects he came up with over the years was that he didn't like Big O because he didn't feel it was specific enough. And so he came up with a way of specifying in a lot more detail the sorts of things that you look at in Big O. And you had to go through and annotate your code, certainly every method call and possibly virtually every line of your code had to be commented with this annotation they had. And then you'd run it through a special kind of a compiler that would pull all the annotations together. And then you would run the program with the particular data set because, of course, different data sets are going to have different performance. And it would come up with an estimate for you for a particular set of data. But if you think about it, at that point, it would have been quicker and easier to have just compiled the program and just run it against the data set and just measure the wall clock time on it and just see how long it takes, right? So he didn't really buy very much with all that extra work, and his approach has never taken off. But it's the sort of thing that might tempt you as you think about it, and you're like, well, this is kind of cool, but I just want a little more detail. But the lack of detail is actually a feature and not a hindrance. We're looking at the big picture. We're trying not to go down the wrong path. We're not trying to measure with a ruler how long the wrong path is or how long the right path is. And we want it to be independent of the hardware. If we want it to be hardware specific, we can use a benchmark. And when you start benchmarking things on hardware, you find that all sorts of odd things matter. Like most hardware, in addition to a particular main processor, they have different sizes of cache. They have several different levels of caches. And whether things fit into your cache or not has a huge impact on the performance. Well, will your program fit into cache? Well, it kind of depends on what else is running on the machine at the time. On a PC kind of machine, someone opens a web browser and you've just wasted your benchmark. You've thrown it away because that web browser is busy doing stuff with the caches and the CPU, and you're not going to know what's going on. Another obvious situation with that is that, and then maybe this one fits even better with the next point, We want it to be independent of hardware, and not just hardware like which processor it is, but hardware like which sorts of caches you have. Do you have a solid state disk or a regular disk? Which model of disk do you have? All those things are going to affect the wall clock performance considerably. And people that do benchmarking, they worry about all that, but then of course their results are so specific, they're not so interesting. We would like something to be independent of the details of a particular problem. This is probably a good example of, suppose you've got something where you're dealing with big arrays. I mean big arrays, tens of thousands by tens of thousands, two-dimensional arrays. Maybe you're multiplying a couple of these things, and you do this kind of work for things. Very big spreadsheets will do this. A lot of engineering problems will do this. There are plenty of problems that do this sort of thing. Well, it makes a difference whether you loop through it by the column and then within the column the row, or by the row and within the row the column. It makes a big difference, and that difference has a lot to do with both the hardware and the type of cache you put in, the cache control hardware you put in. We're not looking for something, if we need that level of detail, we need to just go ahead, pick particular hardware and run benchmarks. And we want it to be mostly independent of data values. The big O we've considered, occasionally we've said something about the order of data values. For instance, with sorts, we've said there are some sorts that do poorly if the data is already largely ordered or largely reverse ordered. Well, that's a particular thing about the data values, but it's not super specific. It's not like, well, gee, with this run of numbers, you get this value, and with this number of run numbers, you get this other big O. That's not what we're looking for. So don't try to substitute big O for benchmark. Use it as to show you through a general approach, the neck of the woods you want to end up in. And if you need more detail, then read into benchmarking, and it can be a very interesting area, but works very differently than big O. In general, big O looks at classes of complexity, such as a constant big O versus a linear big O versus a square of big O. And recall that it ignores constants, and a lot of people don't like that. They want to put the constants back in. But that's really getting away from what we're trying to accomplish. We're not looking for small changes, we're looking for big changes. So you might remember this diagram. We hit this pretty early in the course. It's based on LaFleur figure 2.9. And basically, we want to decide which of these sorts of beasts we have. Do we have something that's constant, like line D? Do we have something that's a log n, like line C? Those are both pretty good. Linear isn't too bad, but it's a different beast. And of course, n squared is another big beast. And there are a few graph algorithms that we looked at that are n cubed, right? And I miswrote that there. That should be big O paren n cubed, not big O of 3, which is just another way of saying constant. Sorry about that. This is the world of conventional programs, the world that you'll probably live in, where, when you start seeing n squared algorithms, you start to get nervous. And that's the world that working programmers typically work in, because even n squared often is too slow to be practical. Go to UPS and say, oh yeah, I can do a better job scheduling your deliveries, but yeah, it's n squared with each package you deliver. They're going to lose interest in a hurry. Even scaling like B does won't be all that exciting for them. But there are people that go further. There are what we call hard problems and complexity. And there are theorists, theoretical computer scientists. They're related almost, they're almost mathematicians. In some cases, they are mathematicians. And for them, the world doesn't get interesting until we're getting above that n squared threshold, or even that n cubed threshold. There are problems out there that are bigger and harder than that. And complexity theorists love these kinds of problems, and they love finding what appears at first glance to be a simple problem, but as you dig into it, you realize it's really hard to solve. We're going to look at just a couple of these real quickly, just so that you have a flavor of them. We've mentioned the traveling salesman problem. Pretty straightforward. Given a list of cities, the distance between each pair of cities, what is the shortest possible route that visits each city and returns to the origin city? Well, in the general case, if we want an optimal path, we have a big O of n factorial. We have to try all the different possibilities. What if I go to point B before C? What if I go to C before D? What if I go to B before D? All those things. There's a special case that only works for Euclidean space. Now, most of us, the reality we know is all Euclidean space. You might say, oh yeah, so it's not really so hard. Yes, but you'll notice that even for Euclidean space, that's a fairly gnarly looking big O there, right? N times log n raised to the big O of constant times the square root raised to the power of d minus 1. You know, you can look up what that is, but it's not, it goes up really quite quickly. This is not a constant thing by error. Then we have what's called the heuristic case, the rule of thumb case. Okay, we've given up on being optimal, right? But we'd like something that works fairly well. And there's an approach to a traveling salesman called plane cutting, and it can give you a big O of n log n. Hey, that's pretty good, right? But only within 5% of being optimal. But that's not so bad. So if you're someone like UPS and someone has some software, they'll give you n log n within 5% of optimal. You'll probably say, well, let's see if that's better than what we're already doing. That's something you probably live with. Here's another one. Usually I spend a whole couple lectures on this, but we had to cut something out this semester. So this is one of the things that got completely cut out. It's called the knapsack problem. And as you read it, you're going to say, well, gee, that's related to the box packing problem. And indeed it is. But given a set of items, each with a weight and a value, determine the number of each item to include in a collection so the total weight is less than or equal to the given weight and the total value is as large as possible. So we want to maximize the value of what we put into the knapsack. A straightforward solution, a naive solution, we have an n factorial big O, which just takes forever. Then there's a technique that I normally spend most of a week on that we couldn't get to this time called dynamic programming, which does better. It has a big O of n, where n is the number of objects and W is the capacity of the knapsack. It also has the limitation that all the weights have to be positive. But, you know, most of the stuff we deal with in this world, like if we're weighing boxes or whatever, they tend to have positive weights. So really not such a big deal. So dynamic programming is one of those examples. This is a big win over a brute force or naive solution, or even over a greedy solution. And it's still practical. So it's kind of a big win. Here's one. It's a chess problem. A lot of these are chess problems. You wouldn't think that chess would be all that hard. After all, it's played on a board that's 8 by 8. I mean, how bad can that be? Here's an example of a chess problem called the Knight's Tour. If you've ever played chess, knights move in kind of an L-shaped pattern. It's kind of an odd pattern. And a Knight's Tour is a sequence of moves of a knight on a chessboard. You get to pick where you start, such that the knight visits each square once and only once. Okay? And this is a possible solution. You can see it starts sort of off center of the middle there, and it shows the various places you land, and it shows the pattern of moves where you end up touching each square, landing on each square exactly once, and then finally landing on your beginning square, because it's a tour, it's not just a pattern. So the big O here is k to the nth, where n is the number of squares on the board. So that's to the 8th. This is a big O, where instead of being n squared, it's to the 8th. Oh, I'm sorry, number of squares on the board. That's the 64th, right? At 8 by 8 board, that would be 64. K raised to the 64th power. So on an 8 by 8 board, there are exactly, let's see if I can find this, hundreds, thousands, millions, billions, 26 trillion, 534 billion something directly closed tours. Assuming a computer makes 1 million moves per second, it would take 1 million years to solve this problem in a brute force manner. Okay? So these things can get big in a hurry when the theorists get clever. Here's a simpler chess problem, and I think it's simpler. And by the way, the United Tour is mentioned briefly in LaFleur. This is the eight queens problem. It's a puzzle of placing eight chess queens. If you've played chess, each side only gets one queen. So this is a problem almost unrelated to the game. But queens can move as far as until they hit another piece, horizontally through the row, vertically through the column, or on the diagonals. They have two diagonals. So they cover quite a bit of distance. And so the problem is to arrange eight queens on an 8x8 chessboard so that no two queens can attack each other. So two queens cannot share the same row, the same column, or the same diagonal. The problem of finding all the solutions to the eight queens problems can be expensive, as there are, let me count this, hundreds, thousands, millions, billions, 4,426,000,000 possible arrangements of eight queens. Now, not all of those meet the criteria. What meets the criteria is 92 solutions. So the goal is to find one of the 92 solutions out of more than 4 billion moves. It's a bit like finding the needle in the haystack. Knowledge about the problem greatly reduces the number of moves you have to consider. So for example, you can start by saying, well, we're only going to use one queen per row, and then just slide queens around in their row. That will not eliminate any good solutions, but it eliminates a lot of failed attempted solutions. And so that's a heuristic, a rule of thumb, based on the knowledge of the problem that makes it much easier, although still not trivial. And there's some larger complexity classes. Traveling, you can apply dynamic programming, which we didn't get to study this semester, the traveling salesman problem, and you get a big O of c raised to the n power. Never good when the exponent is a variable related to the size of your problem, right? So if that's UPS delivering boxes, n might well be the number of boxes they deliver, large number. Or here's another one, traveling salesman problem solved with brute force, as we've mentioned before. It's an n factorial problem. Those are complexity classes that we didn't bother to graph at the beginning of the semester. And theorists love working with problems like this, but in practice, they're just too long. People don't try to implement them or don't run them in useful ways. It's not the sort of thing a company would buy because it would simply soak up too much hardware. Well, hopefully you've enjoyed thinking about where you can go with Big O. And I've got one more video for you that someone else made that's a really cool video. It's listed right after this video, and I really encourage you to watch it because you will think about computing and general and Big O in particular in a different way than you do right now.